Welcome to the first ever RocketTech Podcast. I'm Justin Fischetti.
I'm Konstantinos Gerontis.
And I'm Adam Kotler.
And today we're going to focus on the recent ULA launch, and then we're going to go over a preview for Falcon Heavy. But let's first start off with what we're working on.
Currently we are working on the LAD. Konstantinos, what is the LAD?
The LAD is the Low Altitude Demonstrator, and basically the whole point is to test some vital functions of what's going to be our main rocket that we actually try to go to space with. But
so why don't we give some background on what we're doing first?
Yeah, exactly. So what we're trying to achieve is creating a liquid fueled rocket that gets to about 120,000 kilometers, sorry. No, it's 120 kilometers, which is just above the Kármán line, which is basically what defines space.
120, is it 120,000 exactly?
The Kármán line is at about 100, but
yeah,
yeah,
we're trying to be the first collegiate team to go to space. So Kármán line would be the definition, right?
Yeah. So one of the parts that's really difficult with doing that is that we need an area to test in, and we also need to prove to the FAA that all of our systems work before we actually go for the attempt. So the way we're going about doing that is LAD, the Low Altitude Demonstrator, which, as the name implies, it only goes to a pretty low altitude, and what it's going to do is basically use the same recovery system, the same control system, and a couple other similar systems that are going to be used in Starscraper, which is going to be the one that makes the attempt to go to space, so that we can prove it's safe.
Give a bit of background on Starscraper. That is the rocket that we're going to be going to space with. That's the vehicle that we should be that should hit space first. That's going to be a liquid-fueled rocket using isopropic alcohol, and what are we using?
Isopropyl alcohol and nitrous oxide.
Nitrous oxide. And we're going to have about 2,500 pound forces of thrust on that.
Yeah.
Yeah.
Yep.
Pound force.
Pound forces.
Pound force I.
Pound force. Yep.
Anyway, so yeah, that and because of certain things, we're going to do a low altitude, like Konstantinos was saying. We're going to we need to demonstrate to the FAA that we're not just going to have like a ballistic missile launching at Los Angeles.
We need to shoot accidentally.
Basically. Yeah. So we're going to be demonstrating that our parachutes work, that our reaction control systems work, stuff like that. So currently we're in the process of designing. We're designing all the hardware, running simulations, and finishing up the software side. So
Justin, you're working on structures, right?
Yeah,
so,
that's correct.
What exactly are you doing on structures?
So right now we just finished up figuring out how we're going to transfer the thrust of the motor to the actual airframe of the rocket. The solution we came up with is using 3 centering rings. They're going to be we're going to use adhesive to attach them to the motor, and then radial bolts to attach them to the airframe. And then we also had to integrate the fin can to the airframe. And to do that, we're actually going to use shared center. We're going to use a shared centering ring, and by that I mean the same centering ring is going to attach the airframe and the fin can to the motor. That way, we're going to decrease the moment on the between the fin can and the airframe.
One of the things worth mentioning that we didn't really talk about specifically is that for LAD, we're actually not doing we're not using liquid fuel. We're using solid fuel, which is why we're using centering rings, and why we're going for a low altitude, because solid fuel is generally less efficient. And the centering rings Justin was talking about are the most common way of interfacing the solid motor to the rest of the rocket, or the launch vehicle.
Yeah. We looked into doing a thrust plate, but that was just not. It wasn't practical, and it wasn't the.
You could do a thrust plate and then 2 centering rings. That's always how I did it back in high school with a high-powered rocket. But this may be different, I guess.
Yeah, we were looking into that, but
why can't you do a thrust plate on the bottom and then 2 centering rings higher on the motor mount?
So there were two issues with that. One, we don't know the exact motor makeup, like how the motor is actually going to be like manufactured and all the parts of it. Yeah, the profile.
So like your man, our dude guy hasn't gotten back to us yet.
Yeah, and for some background for the listeners, we're getting a solid motor from a source, and we haven't had the exact specs yet. So we're kind of designing around what we think it's going to be.
Yeah.
But
Okay.
so yeah, when I ran all the calculations, using adhesive to attach the motor to the centering rings, there's plenty of surface area, and we found an adhesive that is able to withstand high temperatures. So we have a factor of safety of like 5, I believe. So
5?
Yeah. So we'll be plenty fine on that. And then the bolts radially, we have.
Why 5 though?
That's just how it came out because
it came out to be 5. Well, then if you come out to be at 5, then why can't you guys go for something else?
Well, I mean,
like,
for this purpose,
because that's not the limiting factor. So the limiting factor, so the 5 set factor of safety was determined by the surface area that the adhesive would be in contact with the centering rings to the motor, and that thickness of the centering rings is actually determined by the shear
force on the
shear force on the bolts radially. So there has to be the center rings have to be a certain thickness, so when the force applied to the bolts by the thrust is when it's applied, the centering rings aren't going to just break. So that's what determined that.
So one of the things that worth mentioning to our less experienced audience is that generally, since the factor of safety or the margin of safety is basically a number you try to get so that you make sure that the theoretical braking force required is much greater than the force you're actually applying to something, so that you basically guarantee it doesn't break during flight. That generally is around just over 1 in aerospace, because you would basically any extra material will increase the margin of safety. So you'll make sure that if a part is thicker, it's less likely to break. But if the part is also thicker than this extra weight that you need to carry into orbit, that decreases the weight you can have for your payload. So generally, for example, for Starscraper, we're actually going to have pretty tight margins of safety. But in this
1.1.
Yeah, 1.1, I think, for ultimate, or rather for yield,
I think it's yield, yeah.
And the good thing with LAD, with the low altitude demonstrator, is that this is just a demonstration. We don't care about how high it goes. If it's above a certain range, we don't really care how high it goes, because it doesn't need to reach space. So we can do something like this where we have a higher margin of safety that may cause us to have less payload, but in this case we don't really have a payload, so it's fine for the specific scenario. But generally the margins of safety are very tight, which is why getting to space is so difficult and why rockets break.
Yeah, if you have, for instance, if you have a stick and it's going to break if you put 10 pounds on it, and that's the point where it's going to break, you're going to want to only load the stick with what is that?
10
Not
pounds.
10 pounds.
Yeah, 9.9 pounds or whatever.
Yeah.
Now on LAD, there's actually 2 or 3 spots where we can reduce mass without necessarily increasing costs because of machining time is free. However, we may not be doing those just because it won't be necessary, and because we're on such a tight time frame, we're gonna push for the quickest, not necessarily the overall best, but we do not need it to be the exact best. For instance, I've been designing an isogrid to go on the centering rings, the thrust rings. Now that's going to decrease mass by probably about 20 to 40%, somewhere around there.
99%.
However, that's not. Yeah, it's going to decrease it by that.
Definitely at least 30.
Anyway, but that may not be necessary because it's more work, it's more time. There's more failure points in the machining process, and
Wait,
it's not
really?
worth. It's not
Is that
worth
true?
For what?
Is that true? Putting an isogrid is going to make it harder, that much harder to machine?
Well, no, it's not going to be terribly hard because we're CNCing everything. But it's just it's a little bit longer. It's a little bit more. If the drill bit breaks, then you need a new one. It's just another thing to do. While otherwise, it's just a disc, which is much simpler.
All right. Well, okay. How about like calculating stresses? Is that going to be? That's not going to be that. That's not going to take that much longer, will it?
No, not very much at all. Our factor of safety on that. I only did back of the hand calculations, but the yield strength for the aluminum. So the force that would take for the aluminum to bend, which the force for the centering ring to bend and to eventually fail is not going to be close to what we're actually seeing. And for the centering rings, we're planning on using 661 aluminum, which is basically just the standard machining aluminum for aerospace.
Yeah. So,
so
Adam,
you guys are working on something. Yeah, you guys are working on something different. What are you guys working on?
We are working on the reaction control system. Konstantinos and I are both working on the same subsystem, and as part of that, we both have to. Yeah, for LAD. As part of that, our first project is to design our own control systems based off of resources provided by upperclassmen on the team and videos online. Yeah. Because it's our first time doing this, so they're going to walk us through the. They're just throwing us in the deep end, having us write our own code, and eventually they're going to walk us through and fix our code for us.
Yeah. So some of what that entails is basically the RCS system is basically shooting out gas perpendicular, or like if you were to picture the rocket from the top view, you basically see a circle. If you were to make a tangent at any point at that circle, that's basically how you're shooting out the gas with the RCS thrusters. And what that does is basically it applies a force in the opposite direction, which is basically how you make thrust in like all of rocketry. That's why the engine is pointed down, because you produce a force upwards. But instead of having combustion happen, you just blow out compressed gas that then is expanded, and that energy is turned into kinetic energy or rotational energy.
So why would you have a reaction control system or an RCS system?
Yeah, so the purpose of RCS is to basically counteract all the forces that the rocket sees, because regardless of whether it has fins or not, especially if it doesn't have fins, it's going to see a lot of forces that are going to start tilting it in weird ways. Like if there's a gust of wind that's unbalanced, it might start rotating the rocket a little bit, and you can't really, if you only have a single engine, you can't balance it out by gimbaling the engine or by
gimbal it, dude.
Yeah, that's something we're
it's a running joke.
Talk about
it's
later.
A running joke with us.
Yeah. So you need something like that applies some rotational force. And the difficulty with RCS is that for us specifically, we use a system that basically is either completely on or completely off. And what that means is, the difficulty with that is that basically we have to calculate exactly how much we have to turn it on for per burst, so that we can reach exactly, if we want to say turn like 90 degrees, we can't overshoot, overshooting is something that's very easy to do. So especially if the maneuver you're making is not due to a force you applied earlier, like say you want to turn 90 degrees, it's relatively easy because say you like turn it on for 0.2 seconds, then you know you're going to have to turn it back on in the opposite direction for 0.2 seconds to stop. What's difficult is finding exactly the angle you've turned, and another difficult thing to do is using the RCS to counteract, like, for example, gusts of wind instead of just forces you applied. So that's some of the stuff we're working on, basically. That's stuff we're trying to figure out with the code.
So RCS, that's exactly what SpaceX uses to turn their first stage booster around after launch to come back.
That's what pretty much every industry, like professional.
Yeah, exactly.
Uses.
It's
like
generally
NASA used it, the Russians used it.
Mm-hmm.
Yeah.
Now, basically, to sum up what you were saying, Konstantinos, and correct me if I'm wrong, but the RCS is effectively there to make sure that we can turn the rocket however we want, or the rocket can turn itself to correct for any unbalanced forces it might see based on drag and wind gusts and stuff like that. And what the RCS is a bunch of compressed gas that is then released tangent to the rocket, tangent
profile.
to the air, tangent to the air frame, which would then induce rotation.
Yeah,
is that correct?
Yes, that's correct.
Yeah.
One thing to note is that for this application, and probably for Starscraper too, we are only using it to control rotation, because there's also pitch and yaw. Other rockets, oftentimes, like Justin mentioned earlier, the Falcon 9, also uses RCS to control pitch and yaw. We're just concerned about rotation for this
Yeah,
application.
wouldn't that be crazy if we could get Starscraper to achieve that horizontal flight profile like Falcon 9?
do a few flips at the end.
Whoa, dude!
Before it re-enters, because why not?
Dude, isn't that why we gimbaled? We're gimbaling. Well, we can get into that stuff later.
We're not dude. I swear.
No, we're
not
gimbaling. We're
anything.
gimbaling Starscraper for sure.
Yeah,
Oh,
Lad. But
Anyway,
Starscraper.
yeah,
Yo,
that's
let's
exactly
talk about
why.
that right now. Let's talk about that right now, okay?
Yeah.
Every time,
That's a good transition.
Every time we want to design something, Justin has to come in and be like, "Hey guys, we should gimbal it."
I mean, most of these don't have an actual application, and most of the time he's
always-
just joking.
Yeah.
But gimbaling is
He's
very, very
always
useful.
always
Yeah.
trying to give Andy an aneurysm because he wants to gimbal everything he sees.
So the backstory of that is it was right during finals, and we were just talking about Lad had just started, and I was like, guys, what if we gimbaled the entire motor of Lad? Because for those of you who don't know, with a prefabricated motor, you can't direct the flow of the propellant without actually moving the entire motor, unless you had a scarf, which
or with like jet vanes, which are we might cover this another time. But it's really hard to
anyway,
control the direction.
Yeah, go ahead.
Super hard science stuff.
Yeah, but anyway, so I was like, yo, what if we put a gimbal on the motor, and then we could gimbal the motor? And I was kind of joking, kind of not. I think it would be kind of cool to do that. There's no reason to. For those of you who don't know,
Okay, you were not joking, Justin.
Okay. For those of you who don't know, gimbaling a motor basically means you can change the orientation of the motor, so you angle the motor basically, and that can let you steer. When we did out the math, it turned out it would be like what, 6 months of work.
Degrees.
It would be like 6 months of work to get
for
2 degrees.
2 degrees.
2 degrees of motion.
Actuation.
Yeah. So now we have the running joke.
Yeah.
Anyway,
Hey, 2 degrees of actuation on both sides. Okay. So 4 degrees.
So
4
generally,
total.
generally, how this is done when you want to control the direction of flow of a solid rocket booster, you use usually jet vanes, which are basically sometimes graphite, sometimes another material that's got a very high melting temperature, and you almost put fins that are tiltable in basically in the stream of the booster, which is also difficult to do because it's very, very hot and the gases are going extremely fast. So yeah.
Speaking of solid rocket boosters, ULA had a launch this week.
And they had solid rocket boosters on their rocket. The
Smooth
Delta
transition.
4.
Yeah.
The Delta 4.
So they launched on January 12th, 2018, out of Vandenberg Air Force Base in California. It was a classified mission, so we don't know the exact payload.
It is called, we do know its name though. It is called the NROL 47. I don't know if I'm saying that right.
Yeah.
NROL 47.
So that is the National Reconnaissance Office launch. Well, the L stands for launch. So it's a super spooky secret satellite.
What do you think they're doing? People are like, oh, they're spying on us.
Well, I mean,
There's more stuff to spy on us.
the military does need
probably,
a lot of
but
satellites for GPS, for
surveillance.
Yeah.
Intel stuff. I mean, it would make sense.
Yeah, it's
I think
common.
they're specifically spying on you, Adam.
They're probably.
Dude, they're releasing waves into the air. You gotta whip out your tinfoil hats.
Yeah. But one thing one thing that we were discussing before we started recording was that it looks like the solid rocket boosters have scarfed nozzles. So you guys want to go over what that means?
So
get it, Constantino.
One of the reasons companies use scarf nozzles. Basically, let me go over what scarf nozzles are.
Explain what's exactly.
So a scarf nozzle, if you look at any rocket engine, any like solid or liquid, you'll see a nozzle at the end that's kind of like looks like a bell. That is used to expand the gases. So basically, you get some of that pressure of the gas to be almost like turned into kinetic energy. The gas is the combusted or burned fuel, rather.
So the exhaust gas.
Yeah, the
like
exhaust
the exhaust
gas.
of a car kind of thing.
Yeah. Well, no. Sort of. Exhaust
your
in a
car's
way,
a rocket.
they're the same because they're the gases that are exiting, but the difference is in a rocket, the exhaust gas is the like in an engine, the pistons in the cylinders are the way you get the energy from the fuel. In a rocket, it's by shooting the burned fuel out, or the exhaust out very fast. Anyways, so the nozzle.
Newton's third law.
Yes, exactly. That's why you have to point it up or point it down. don't point it up.
Wait. Is that the 2 + 2 is 4 - 1 is 3 quick math?
Dude, no, I think that was
that is exactly what it is.
That was Bernoulli. Anyways, so a scarf nozzle, what it is basically you take a nozzle, you look at it from like any angle, and like you slice it like diagonally.
Not 90 or like 180 though. Not those.
Yeah, that would just
any angle that's not those.
Yeah, pretty much. So the reason you do that is
it is scarves.
Yep. Thank you.
Yeah, I just wanted to make sure. I just found a photo that shows that it's scarf.
So the reason you want to do that is because that basically causes the gas to push on one side of the nozzle more than the other, because the other side is not there as much if it's cut. So what that does is, if you were to picture thrust as a vector, generally in a rocket nozzle it goes straight up through the engine. With a scarf nozzle, it's kind of tilted with the scarf. So the reason you do that in big rockets is because you have the solid rocket boosters generally are on the side of the rocket. If, say, one of them was to have an issue, maybe it's producing less thrust than it was supposed to, or it's off completely, if you had the liquid engine in the middle and two solids on the side, and one of the sides turns off, you would have forces on the middle and the left side, but none on the right to counteract the one on the left side. So your rocket would start spinning.
Scarf nozzle, correct?
Yeah, without the scarf nozzle, you basically would have a rocket that's very angry, and it would start spinning. With a scarf nozzle, because the vector of thrust is tilted slightly, it's tilted to go right through the center of gravity of the main part of the rocket, so that even if, say, the other side was not to produce as much thrust, you would still have, it would still basically be going through the center of gravity, so there's no torque applied onto the rocket, so it still goes mostly straight up. And then also
it's mostly straight. And also with your RCS and your other mitigation
and your liquid
systems,
liquid engine is usually gimbaled.
It makes it
so that say one engine turns off, one of the solids turns off, the liquid engine can kind of point towards the solid that is on, so that so that your center of thrust is aligned with your center of gravity, which is exactly what you want. That's the long form of it.
Yeah.
Or short form, actually.
So if anyone's confused on the what a scarf nozzle would look like, if you've ever seen one of those old movies about ninjas or samurai, when they take their swords and they slice bamboo, how that is, that's effectively a scarf nozzle. How that has that angle on a
exactly. That's
that diagonal profile.
In this week's news, there was a SpaceX launch that kind of had
more
that's in the news. Yeah, also secret-y. Do you guys want to talk about that a little bit?
No. No, I do not.
Well, I guess not.
All right, that's the podcast. Thank you for listening.
All right, thanks for listening. All right, see ya.
No, but yeah, it's pretty interesting. So to recap, SpaceX launched a classified payload. Well, who is it made by? The Norman Group or something like that?
Northrop Grumman.
Northrop Grumman.
Northrop Grumman.
Okay, so SpaceX launched what we think is a satellite. We're not really 100% sure.
It's probably a satellite.
Probably a satellite, yeah. Anyway, they launched it, and there was because it was classified, there weren't cameras on the second stage or anything like that, and SpaceX's usual transmission of the launch ended after the first stage landing. And what happened was so let me make sure I have this right. There was one confirmed good orbit. So we know that the satellite, which was labeled USA 260, orbited once. So
280.
We know that was it 280? You said
it's 280.
Oh, okay. Yeah. So we know that the satellite orbited once because it was picked up by an independent satellite tracker.
I believe so. Yeah. Which is generally how orbits are confirmed. Also, if you have no telemetry.
So that was confirmed. So we know that it was a good orbit, and we also know from SpaceX's comments that the Falcon 9 did everything it was supposed to, including the second stage. What is interesting though is that people claim that they saw that the second stage and the satellite burnt up and fell into the Indian Ocean, which doesn't make sense because unless there was a purposeful deorbit from the original orbit, there's no reason that it would have fallen out of orbit.
Yeah. Also, I've been doing some research, and I've found a video of someone from Northrop Grumman during a press conference, and basically SpaceX released a statement saying that on their part they did everything right, but they couldn't say much more than that because of the classified nature of the launch. During the press conference, the Northrop Grumman person got asked the question whether or not they could confirm that the payload was in orbit, and they said they could not say anything other than refer them to the SpaceX comment, or to refer to SpaceX.
Yeah.
Which is very generally in these situations the Department of Defense or someone who's paid, if it's a satellite that has been paid with taxpayer dollars, generally they confirm or deny if the payload went into orbit. But this time they kind of just referred to them to SpaceX, which kind of makes me think that, it is kind of spooky because it's very...
It makes you think that what?
It makes me think that it probably was something wrong on Northrop Grumman's side, who manufactured the satellite or the payload.
Now, what's interesting is normally SpaceX will manufacture the part that attaches the satellite to the second stage. But in this case, how do you say it? Northrop Grumman?
Northrop Grumman, yeah.
Northrop Grumman.
Grumman.
Grumman?
Northrop?
Grumman?
Grumman.
Gorman? Grumman.
Grumman, okay. Northrop Grumman, is that right?
Northrop Grumman.
My boy, in this case, my boys over at NG produced that.
Well said.
So it's fully possible that the Falcon 9 could have done everything correctly, including the second stage getting to the correct orbit, but NG didn't manufacture the coupler correctly, so the satellite never actually detached, and it fell, which means it could have fallen back into the ocean with the second stage. But
yeah, it's a good point.
It's unlikely that the second stage would do a deorbit burn with the satellite still attached. That's very unlikely.
So do you think there's a possibility that they're just still stuck together in orbit?
I think people saw the second stage come down though.
Yeah, Northrop Grumman's the company that made the stealth bomber, right?
The what?
The X-37B.
The Spirit.
Oh yeah. Northrop Grumman is a huge. They're a very big aerospace company that works with the Department of Defense. Have worked with them for a very long time. They are in aviation and in aerospace in general.
If some of the audience doesn't know what the stealth bomber is, I just suggest you look it up for some eye candy.
It's beautiful.
It's so beautiful.
Stealth bomber is some of the finest piece of aviation.
Finest piece of metal.
It actually flew over the Alabama game. The Alabama football game.
A couple times. It is.
Do you guys know that it's designed to self-destruct upon failure?
Did not.
That's incredible.
Is that on purpose?
It's on it's on purpose. So that enemies don't get our secrets.
Yeah. Actually, that's probably also partially due to the what was it?
Space race.
The U2. The U2. I'm pretty sure there was a very big problem back in I think the 60s.
Explain the U2.
Was that also designed? Was the U2 also designed to self-destruct? U2 was It was a problem. Okay.
Yeah, the U2 was a reconnaissance aircraft. It flew very, very high. I'm pretty sure it was up to 70,000 feet, which is freaking high. And
not as high as Starscraper's gonna go.
Truth. It was also some very fine piece of metal. So during a mission, I forget if it was shot down or somehow there was a failure.
It was I don't remember.
It landed in USSR territory, and
so then they got the technology.
Yeah,
during
so
the Cold
they
War.
got some tech. That's probably something that influenced the self-destruction feature of the B2 because that was.
It was shot down. I just looked it up. It was shot down.
Yeah. So.
Did you guys know that the B2 is modeled after the profile? The cross-sectional profile is modeled after a Falcon.
The what? The what was?
The cross-sectional profile.
Not the Falcon 9, an actual Falcon.
Yeah.
It's what is it? It's the Falcon in the western United States that has it's the fastest animal in the world.
The peregrine falcon.
The peregrine falcon. There it is.
My that's actually my favorite animal. Yeah.
Nice. Mine is a Turritopsis nutricula. But we'll talk about that another time.
What is a Turritopsis?
It's a jellyfish that also turns into a plant when it's scared and almost dead. So it regenerates.
That's ridiculous.
It's basically indestructible, but not. But like pretty much, it's an animal and a plant at the same time. What's cooler than that? I mean, I guess the falcon's pretty cool. But
yeah.
Goddamn.
Where were we?
We were talking about the B2 bomber. Adam,
we were talking about
the U2, and then we went to the Lockheed U2.
Yeah.
Oh, we were on ZUMA. Yeah.
Right, yes.
So it's just kind of interesting that, and this blew up. So originally it was reported by a smaller outlet.
No, not physically,
places
like in the news.
Yeah. The news of this blew up. It was originally reported in a smaller outlet, and then people like Forbes and Bloomberg, they took it and ran with it. It's quite interesting because if Falcon 9 did everything correctly, that's really good on SpaceX's part, and I'm happy that that is that because that means the space exploration can continue to push forward, and we'll get into that later. But that's really good. It's interesting that happened. Now, there's plenty of conspiracy theories going around, such as like this was intentional and it's actually hiding somewhere, or something like that. Or it's like on the ISS or something like that. It's actually docked to the ISS right now, but we don't know that. That would explain not having it. But then again, Dragon just came home, so that's some more news. Okay, we should hit that too.
Yeah, that's a good point.
Okay, and then in other news, Dragon came home. You guys want to talk about that?
Yeah.
Oh wait, did you guys have more on Zuma? Sorry about that.
I think
I did.
Okay,
like it's not that pertinent, but like Zuma happens to be the last name of the president in South Africa.
That is true. I just looked that up.
South Africa, from where Elon Musk was born.
That sounds like not coincidence.
It's probably just a coincidence.
Adam, I think you're onto something. I think you're definitely onto something.
Dude, maybe Elon Musk is running for president or something.
Dude, I
Musk
wish.
2020.
Anyways,
Dude, Musk 2020.
Anyways, going to the Dragon. Do you guys want to talk about its history and why it was on the ISS to begin with?
Sure.
Yeah. So Dragon, SpaceX's original answer to interplanetary travel.
Really?
Yeah,
Pretty
it was
much,
their
yeah.
first, but they're not doing it anymore. That was their
Because now
that's
they
their
have
current plan.
Yeah.
Because they have the ITS, right?
Yeah, and yeah.
The ITS. What is ITS?
Interplanetary transport system, I think. Probably something like that.
Yeah, I think that's it. That's it. Interplanetary transport system. What Constantino said.
Yeah. So the Dragon was basically a really. It's a capsule. It's a really cool capsule though, because it has propulsion on it for. Well, one of the things capsules have to do is they have to break off of the main launch vehicle if there's a problem. Generally, there's an LAS, which is a launch escape system, which is basically like a really big stick of solid rocket fuel on top of the capsule that lights up and throws it off it in one direction away from the problem. But SpaceX approached.
Let's go back to what a capsule is.
Yeah.
So
yeah.
too basic.
Fair enough. Adam, want to?
So you guys are familiar with the? You guys are familiar with it, for those who are familiar with the lunar module, during the Apollo missions back in the
60s.
During the 60s. So essentially, you have the payload, which would be the Dragon capsule, and that's what carries the crew. And such a vehicle is the vehicle that is designed to land on a planetary surface. And during the Apollo missions, it was a lunar module which landed on the moon. And the Dragon is essentially SpaceX's iteration of that, but for Mars.
What a capsule is Dragon is a capsule, and a capsule is basically what goes on top of the first stage rocket booster or on top of the second stage. It gets thrown into space, carrying stuff, whether it's people or cargo, and it can do stuff with that. So it can maneuver its way to either dock with the ISS or land on the moon or land back on the Earth.
Also known as a payload.
Payload.
More commonly known as.
Yeah, but if the payload is not something that is needs to be like super safe, and if it's bigger than a capsule, it usually is just around. There's a fairing around it, which is basically like an eggshell almost, really big eggshell that protects it from aerodynamic forces while it's in the atmosphere, and then breaks off after it gets to space. So if you listen to or if you watch a Falcon 9 launch, there's a checkpoint where there's fairing separation, which is when that eggshell thing basically breaks apart and the payload is free to touch space.
But so Dragon basically got shot up with a Falcon 9, and it docked with the ISS and delivered food, water, or actually I don't know if it delivered water. It delivered food, science experiments, and all sorts of stuff. And it stays there for about a month connected to the ISS. The astronauts have time to take everything out, organize it, yada, yada, yada. Then after about a month, they reload it with all the finished science experiments, any waste. So a lot of astronaut poop goes back. And they load it back, and then the Dragon will separate from the ISS, the International Space Station, and then come and fall back into the ocean, effectively.
Yeah. Also the capsules generally have RCS systems on them. That's how they maneuver, because it's an easy, low thrust way to move around without combustion. But the Dragon also happens to have, as we mentioned earlier, engines that do work with combustion that are for higher powered applications.
And those are used to save the payload, correct?
Yeah, those are used for first off, if there's a problem, for the capsule to break off of the rocket or the launch vehicle while it's still ascending or blowing up, and then they're also used for softening the impact when it's approaching the ground very, very fast.
I thought they weren't doing propulsive landing anymore.
I think...
Yeah, that's why they're not using Dragon anymore.
Yeah, that's why... That was kind of a concept. That's not... Yeah, it's not really going to be used anymore, but it was cool. Basically.
Yeah.
Imagine the same system that lands the Falcon 9, but on a capsule. Somewhat.
Yeah, so, like, in case you guys are wondering what SpaceX's new plan for getting to Mars is, it's the ITS launch vehicle. We mentioned it earlier, but so you guys know how the Falcon 9 has 9.
No, I think is it still ITS or is it isn't it BFR now?
I think it's turned to BFR. Yeah.
Wait, really?
Yeah.
Did they change it again?
Yeah, you haven't heard of BFR?
Yes, I'm looking
yeah.
at it. Wait, so the ITS uses 42 Raptor engines. How many does the BFR use?
ITS isn't a thing anymore.
Yeah.
It's all BFR.
Right, but the
I think the
ITS
BFR
was going to use 42.
I think it's 39,
but the BFR is how many?
39, 36, something like that.
Okay.
Yeah.
Generally, resupply missions. So that the Dragon's mission was a resupply mission. Generally, resupply missions in the past have been, or the past couple decades, have been, or past decade, I guess, after the shuttle program ended. They've been carried out by the Russian Soyuz capsules, which is the basically Russian capsule, which is also how astronauts get to the ISS. They still do using that form of transport. But SpaceX now provides a form of transport for payload, at least for the US, which is a pretty big step because NASA isn't really getting all that much funding.
RIP.
In that sector at least. So they're stepping in and they're doing that. For now they're doing payload only, like not or they're doing cargo, they're not doing humans. But I think in the future it's planned for like maybe possibly doing humans also.
It's not so like late 20s.
It's not for a while. At that point I don't even know what the future of the ISS looks like, so.
So in a little bit of history on resupply missions through SpaceX. In 2008, SpaceX won a NASA contract for commercial resupply services, which basically means that SpaceX will launch all of the food and clothing and scientific experiments up to the ISS for NASA, NASA's Commercial Orbit Transport Service. So that's why you'll see the launches denoted as CRS dash the number of launch. And so for ZUMA, I believe ZUMA was, I'm not sure.
What are you looking for?
What ZUMA's CRS something. Oh, it wasn't a CRS, no.
ZUMA was, I think, like...
No, yeah, it wasn't a resupply mission.
Yeah, it was an NROL.
Yeah. But anyway, for ZUMA's launch, they were successfully able to land the first stage booster again. This is the 21st. So they were successfully able to land the first stage once again. This is the 21st time they have done that, making it 17 times in a row that they have landed the booster. This is truly the way to get space travel, the cost of space travel down. Falcon Heavy, it's finally here.
Falcon Heavy.
Yeet.
Woot.
So after about 7 years.
Yeah.
A long time.
Aerospace time is normal. Yeah, so after about 7 years of waiting, so SpaceX likes the Falcon 9 and all, but what if you have a bigger payload? Or you want to send it further?
When mommy and daddy love each other.
So what the Falcon Heavy is, if you look at something like the Delta IV and the Delta IV Heavy, it's basically the same thing. It's a similar thing. The Falcon Heavy is like the Falcon 9, but with another 2 first stages strapped to the side. Basically that allows you to do is carry a lot more payload, or basically it allows you to get the second stage to a much higher orbit with its payload. And then you still get the benefit of landing the first stage, or in this case the first stages, because all 3 of them come back using the same approach as the Falcon 9. They land on barges and on land.
The center booster is going to land on one of their drone ships, the drone barges out in the sea, and the 2 side boosters are going to come back and land on LS1 and LS2. They're going to come back and land. The 2 side boosters are going to come back and land on land. Hopefully, all 3 will land, and SpaceX is going to send a Tesla to Mars. Today we're recording this on the 14th. And today they had just done a test. Was a wet practice run. What do you call that?
We do those.
Yeah.
Water flows?
No,
the cold flows.
Yes.
Yeah, they did.
Is it the cold flows?
It is
the cold flow.
We
also do water flows.
I don't think that's technically what they call it, but
it's basically flowing everything that's going to be flowing, but without igniting it.
Yeah. So today on the 14th, they ran through their loading procedure for fuel and ox, and everything appeared to be nominal. So it looks like they're go to test to run the static fire tomorrow on the 15th. Which, for those who don't know, a static fire is basically you launch the rocket without launching the rocket. So you strap the rocket down and you light the engines and see if everything goes. Lots of fire at the bottom.
Everything is nominal.
Yeah, lots of fire at the bottom, not lots of fire at the top. And that basically prepares, that tests out all the systems, make sure they're good for launch, and then they'll be able to launch.
Yep.
The launch is slated for tomorrow, right?
The static fire.
Originally, the launch was gonna be tomorrow.
Originally, the launch was
basically, in general, in rocketry, the closer you get to launch date, the more it moves away from you. But the closer you get, the further you get. But usually, as you approach it, the amount it goes away is less and less.
So divide by 2 each time.
Yeah, a few months ago, it was supposed to be just before New Year's, or just before New Year's. Then as we approached it, a couple of weeks before that, it got pushed back a week or two. Then now it's getting pushed back a few days at a time. So yeah.
So essentially, they delay it.
It's like an asymptote.
They do the delays frequently, but each delay is
shorter.
A shorter time. So. Eventually, the tests will occur and the launches.
It's a long way of saying it keeps getting delayed.
Pretty much, yeah.
Yes, but each delay is shorter than the previous. So that allows you to remain hopeful.
So now, the significance of Falcon Heavy is that this is going to be the most powerful rocket that is currently working. What's going to be great about this is going to be able to launch much heavier satellites or much more satellites to higher orbits for less money, making everything cheaper and more accessible to people to companies who may not be able to actually afford a normal launch. This is significant because it's going to open up the skies for more people. And can Falcon Heavy get to Mars? Yeah, it's good.
It can send certain payloads to Mars. Depends on what the payload is. Yeah.
And because we can now send stuff to Mars. Not that we couldn't before, but
cheaper.
Now a private corporation. This will be Falcon Heavy launching the Tesla Roadster. For those who don't know, the payload on this test flight is going to be a Tesla Roadster.
Because Elon Musk is freaking cool.
Yeah. And more technical because they don't want to charge someone for an untested rocket, which I think is a little silly. I think they should just give a discount and be like, hey, we don't really know if this is going to work, but there's a chance that you can
give us
Mars.
$50.
Yeah, give us $50.
We'll do our best.
Buy me a McChicken and we're good. Yeah. But anyway, SpaceX is sending a Tesla to Mars, which is pretty freaking sweet.
It is really freaking sweet. Yeah.
But yeah,
according to Elon Musk, first test is probably going to fail. As is what happens with most first tests, because you can't test all your systems and subsystems prior to actually flying.
Yeah.
We can hope for the best, but
unfortunately, it might be a waste of a sweet Roadster.
the first 3 Falcon 1s. So that was the very first. Those were the very first rockets that SpaceX launched. All 3 of them failed.
And
it was only until the 4th one that they got it correct, which was incredible because they needed to get that for the NASA. They needed to launch successfully for NASA to give them a contract.
Wasn't that also pretty close to getting them bankrupt if they failed that launch?
Yeah, they wouldn't have been able to keep going.
Yeah. So, kind of
Elon Musk is just doing things.
He's always doing things, indeed.
He's just doing things, dude.
So to expand more on the Tesla Roadster, basically what they did was take Elon Musk's personal red Tesla Roadster, the original one, first electric. So they basically put that in the fairing attached to the coupler, which will attach to the second stage, and they're going to launch it. One thing interesting in the photos that they shared was you can see compressed air tanks. So what would you call
GN2 bottles? Well, I guess
we don't
GN2
know.
Actually, I think is it just like it might just be monopropellant for the RCS. Maybe.
So it actually could be GN2 bottles.
Well, they wouldn't use GN2, but it could be propellant for the RCS. Yeah.
Anyway, there were gas tanks. So on the inside of the fairing, which is really interesting because that means that it might be that they're trying to recover the fairing.
Yeah.
Now they do use RCS to slow the descent of the fairing and to control it, but it's possible they could also use that same system to catch the fairing.
Yeah. The fairings are they're most likely going to be coming down at a much slower speed because imagine like
drag.
Yeah, imagine throwing. It's the difference between throwing down a steel pencil or an eggshell.
A steel pencil.
Yeah,
what
like as in like the first stage.
Is that Constantinos?
It's
because
like the first stage
in
and like the fairing. Like the steel pencil is like the first stage. It's like it's a bunch of metal in a stick with a very low profile, which means that there's not a lot of force pushing on it from the air, but there's a lot of gravity pulling it down.
It's like dropping a hammer versus dropping a feather.
Yes, maybe not so extreme, but pretty close.
Have you guys seen the video of?
Yeah, in the vacuum. Sick.
Yeah.
Anyways,
on the moon on the moon.
What?
Have you
on
seen
the
that?
moon?
Yeah, they did that.
It'd be the same thing as being on the moon.
But one of the astronauts.
The fairing, the fairing is comparable to an eggshell. It is strong yet light, but it's also it has a very, very big surface area surface area to weight compared to the first stage, which means that it's going to have a lot of resistance going through the atmosphere, and hopefully going to come back slower and get caught in a huge net on a boat that SpaceX owns.
About 2 or 3 weeks ago, someone spotted the ship that SpaceX owns now has these really wide, long arms on them. So if you can imagine like big spider arms that are inverted so that they're facing up.
It's a good way to describe it.
What people think is going to happen. Yeah, so the ship actually looks like if a spider were on its back, but with only 4 legs. And what people think is happening is a net is going to be strung between those legs, and they'll catch the fairing like that.
That is
ambitious
very cool.
That'd be pretty dope. By the time this releases, we will know whether the Stagfire was successful or not. We'll post that in the show notes to let you guys know, and post some links to some other places you guys can check out some information. One thing that I find interesting about Falcon Heavy is it kind of has an expiration date with BFR. So for those of you who don't know, BFR is SpaceX's concept for a massive rocket that will be able to do everything Falcon Heavy can.
Do you think it has an expiration date? Does
it have the same concept? Like
it's the same concept. Yeah,
the same concept.
Do you think? What about like smaller payloads or like more frequent launches for like smaller payloads?
Sure, but then they would use just Falcon. They would use Falcon 9.
What about like
That's why
in
I'm saying.
between?
But like, then use BFR because BFR is going to be so cheap because everything's going to be reusable.
Well, I mean, I see your point.
That's why I like. I'm almost a little confused on why they would put so many resources into Falcon Heavy when it has a clear expiration date with BFR.
I mean,
like I
don't
know
think
they
it's
need
super
it for
clear,
now. They need.
And they got to build up, I guess.
Yeah, they also have
Can't
to build
just
it
go
up.
straight to BFR.
Like the BFR is a very like big and like ambitious approach, and they don't really have anything near it. I guess it's like almost like a stepping stone, possibly.
Yeah. Plus, like perfecting the systems on Falcon Heavy will make it easier to integrate those systems onto BFR, or whichever systems that they can integrate into BFR from Falcon Heavy.
That's true. I just find that interesting. That and also it wasn't supposed to take this long. Obviously, we were supposed to have it years ago.
Yeah.
But, at this point,
but engineering takes time. That's usually the case. Lots of delays.
Obviously, this time, first podcast, there's a lot we covered, but there's so much we didn't cover. Some of the topics we're going to talk about over the next few episodes, over the entire course of the podcast, actually, are going to also include like topics like Blue Origin, their new vehicles, the Electron from Rocket Lab, maybe other
what
countries,
NASA's up to,
what NASA's up to, what Russia's up to, what China is up to,
what North Korea is up to,
what China's up to.
We might even honestly,
scoop on North Korea.
We'll cover North Korea.
Yeah, why not?
I mean, we kind of have to.
Yeah.
Yeah. They're kind of doing rockets over there.
Yeah. So that's some of the stuff you can definitely expect from us, and also some specifics, as we mentioned.
We'll also cover small aerospace industries like Firefly, Arrow, and Arca. When we talk about Arca,
and what the aerospike is. And also what gimbaling.
I can't wait for the aerospike.
Gimbaling.
I can't wait till we talk about the aerosspike. But yeah, just a few things we have in store for our audience in the future.
Indeed.
Are we ready to wrap it up, guys?
I think so.
If you guys have any suggestions on how we can improve the podcast or anything that you guys like specifically, definitely let us know. Yeah. Our email address is RocketTechPodcast@gmail.com. You can find that in the show notes also.
You could also find that information on our Kickstarter and Patreon pages.
Yep. And there's also going to be more information posted on our Instagram pages. You might get some tweets from our Twitter. We'll have all the links.
Follow us at... Oh, go ahead, sorry.
Yeah, we'll have all the links in like a... Here. Under here. Points down, even though there's no camera feed. Anyways, go on, Justin.
In the show notes, we'll have the links to all of our social media, all of the links, Kickstarter and Patreon. If you guys want to support us, that'd be really helpful. We're looking to get some equipment to improve sound quality and streamline the process. So definitely check out those pages. Follow us on Twitter at RocketTechPod and on Instagram at RocketTech Podcast.
And we've also set up a Discord community.
Yes.
If you want to figure out if you want to learn more about entering our Discord community, go to our Patreon. So yeah, thank you guys for listening to the RocketTech Podcast. Stay tuned for our next episode, which will be released the following Sunday. I'm Adam Kotler.
I'm Konstantinos Durantis.
I'm Justin Fischetti. Keep your fittings tight, boys.